Hello students, welcome to another tutorial on linear motion. In this tutorial, we're going to look at this interesting question. I hope you guys can just try to read through the question, understand what we're looking for, and then we can continue together. Okay, so let's quickly read the question and see what they're saying. A train approaching a station does 2 successive half kilometers in 16 seconds and in 20 seconds respectively. Assuming that the retardation to be uniform, find the further distance the train runs before stopping. What are they telling us? Well, they're saying we have this train that is approaching a station and it covers 2 successive displacements. So these are half kilometers each in 16 seconds and in 20 seconds respectively. So in other words, what we're seeing is that this train does half a kilometer in 16 seconds, and then it does half a kilometer again in 20 seconds this time. This is deceleration, so this train is approaching a train station. But what they want us to find is how far it actually travels, it goes before it finally stops. And then we're being told that the acceleration throughout this motion, the acceleration was uniform, but we don't know what it is. So that has to be a hint. We probably would need to find that acceleration for us to be able to determine the stopping distance, how much further it will go before stopping. Okay, let's see what we have to do. Let's try to sketch a velocity time graph to see exactly the behavior of this train, to just help you guys look at the question from another perspective. So here, basically what they're saying is that the train starts from some point, its velocity is reducing until when it eventually stops. But it does the first half a kilometer in 16 seconds, and it does the second half kilometer in 20 seconds, meaning if this is the 0 point, the time now is going to be 36 seconds at that particular point. But what we want to find, what the question is asking us to find, is how much further the train travels before it comes to rest. So this is the part they want us to find. They're telling us this is 500 meters. This is another 500 meters. But what is this extra distance that the train will have to cover just as it comes to rest? Now, how do we work out such a question? Well, start slowly. Look at what they've given you. They've given you this displacement here. How would you get this displacement? So start by evaluating motion in the first part. In the first half a kilometer, we want to evaluate what is happening here. Well, notice one thing. Our goal will be to find the acceleration, the retardation that is going to be acting along this. Since it is uniform, it will be the same throughout that part. So we want to kind of determine what that deceleration is. But it's not enough for us to just look for the deceleration on its own. We have to look for a second quantity. In this case, we're also going to try to determine the initial velocity. If we know the initial velocity, we know the deceleration, it will be easy for us to determine the distance that we're looking for. You'll see exactly what I mean with that. But let's try to see how we can determine these two quantities. So let's look at the first part. In the first 16 seconds, what is happening? Well, since I'm given what the time is, I know what the time is in the first 16 seconds. That's 16 seconds. I also know I'm interested in the starting velocity, so I'll keep it. I'll hold on to it here. So hold on to it. Apart from the initial velocity, we're also given what? The distance. So let me say the distance in the first 16 seconds. Let me label it just x1. So we know what this one is. It covers 500 meters in the first 16 seconds. And what else? Anything else here? Let's just see. We have, basically we're also interested in knowing what the acceleration is, the deceleration in that first part. So we'll just hold on to it as well. So when we look at this, we've got no interest in the final velocity after that 16 seconds. So we want to find an equation that relates this without mention of the final velocity. If we get an equation that involves the final velocity after the 16 seconds, it means that we might have to find it as well. We might have to take more steps than necessary. So let's see how we can relate this. The only two unknowns that we have, initial velocity and acceleration, are actually the two unknowns that we want to use later on to determine what the question is asking us to find. So here we see that the equation of interest is going to be S is equals to, let me say not S. So in this case, I'll use X to mean my displacement. So the displacement X is equals to UT plus half AT squared. So here, X is the displacement during that 16 seconds. U is the starting velocity. T is the time that we're looking at, which is 16 seconds in this case. A is the deceleration. So X here is that distance it covers, that first half kilometer, which is 500 meters. The initial velocity, we don't know what it is. We're kind of looking for it. So we'll keep it as 0, but we know the time is 16. So this is plus half. The acceleration, we don't know what it is, but this is 16 squared. So if we simplify this expression, we now have 500 is equal to 16u plus, then 16 squared is going to give us 16 squared is 256, then divide that by 2, we get 128a. So this becomes our equation when we simplify it further. So we can divide through everything by 16, so to just reduce it a little bit. We see that we're going to have 31.25 equal to u plus 16 into 128 goes 8 times a. So this becomes our equation 1. Let's hold on to it. We notice that here we have an equation. Let me not do it here. Let me just make u the subject of the formula here. And we see that u becomes equal to 31.25 minus 8a. So this can be my equation 1. Okay, so it doesn't matter whether you keep the first one or you keep this one here that I'm holding now. Doesn't matter. You see that we'll still need to use this equation. Doesn't matter where you leave it. Okay, so with this equation, we see that we have two unknowns. So what it means is we need to come up with another equation that has the same two unknowns, that starting velocity and that acceleration. Lucky for us, we actually have the means of getting the second equation. If we look at our question, we notice that the question talks about a second displacement, a second half kilometer, which took place in 20 seconds. But since I want the initial velocity to still be the u, if I just looked at the 20 seconds that followed, my starting velocity will be here, so that if I wanted to use the 16, but this will create a new variable that I kind of don't really want to be involved with, because I want this to take as fewer steps as possible. Because of that, I am going to take my starting velocity to still be the same point as in my first case. In other words, I'm going to evaluate the motion for this part up to that point. So I'm going to evaluate this for the first 36 seconds. So this will kind of include the first 16 plus the 20 seconds that followed, so that my total displacement during that 36 seconds is going to be the full kilometer. The deceleration is the same, since the question says that throughout this, the deceleration is maintained. So if I try to evaluate the motion in that time frame, 36 seconds, using the same equation, notice that now what I'm looking at is, my equation is S. So I'm not using S, I'm using X for displacement this time. So X is equals to UT plus half AT squared. Again, X is displacement, starting velocity, time, acceleration. So this is squared. My displacement in 36 seconds is that full kilometer, 1,000 meters. My starting velocity is 2u. My time this time, we're evaluating motion in 36 seconds, plus half of the acceleration times the time, which is that 36 squared. If we simplify this, what we now get is 1,000 equal to 36u plus, so we square the 36 and then get half of it. We're going to have 648 multiplying the acceleration. From here, we can reduce this further as well. We can divide through by 36. If you choose to divide through by 36, what you're going to have here is going to be 27. This can be 0.77, but basically you're going to have an 8 at some point. And then the other side, yeah, but we can just write it as 27.8, just to get at that point. Okay, so if you divide this by 36, what we're going to have here is u, then 36 into that is going to give us 18a. So we can keep this as our equation 2. So from here now, we can work out equation 1 and equation 2 as a system of equations, or we can substitute the equation 1 into equation 2 so that we work out this for acceleration. If we did that, equation 2 would now become 27.8 is equal to 31.25 minus 8a plus 18a. Notice that where there was u in my second equation, if I was to go back, where there was u here, I've plugged in this expression. So this is my expression for u. I've substituted it here so that equation 2 now comes to look like this. All this is basically just u. So I've substituted here. So if I simplify this now, what I have is 27. So I'm going to just remove the brackets here, group the like terms. What I'll have will be 27.8 minus 31.25 is equal to, I'm going to subtract this 2, so I'm going to have 10a. Simplify this further, make a the subject of the formula. What we're going to have is going to be 10a is equal to, so when we make the subtraction there, this is going to be minus 3.47. Divide both sides by 10, and this becomes negative 0.347 meters per second squared. So this has given us the acceleration, but the acceleration is not enough. Remember, our goal is not the acceleration. Our goal is the further distance. But to get that further distance, the acceleration will not be enough. Regardless of the equation we want to pick, the acceleration is not enough. So what we choose to do here is to get an extra term. In this case, we're going to use the initial velocity. So from equation 1, initial velocity was given by 31.25 minus 8a. But we know what acceleration is this time around. So you can say this is 31.25 minus 8, multiplying the acceleration, negative 0.347. So if we simplify this, we get the initial velocity as 34.03 meters per second. So this becomes the initial velocity of this particular motion. But now that we have the initial velocity and the acceleration, now we can actually continue to get what the question was asking us to find all along. What are we trying to find? The further distance the train moves as it comes to rest, this part here. So this is what we're looking for. So to get this, what we're going to do is that two methods we could have used. We could have tried to find the velocity at this point, because we know the velocity here. Now let's take that to be the final velocity. It's going to be 0 at that particular point. So if we knew the velocity here, we could have said this velocity changing to 0, what would be the distance it will have to cover? Since we know the acceleration, we could have easily found it using the velocity at this point. But we can use another method. The method we're going to use, since we know the starting velocity here, we're going to say this is our initial velocity, that 34.03. So we're going to say if this is our initial velocity and that is our final velocity, and our acceleration is negative 0.347. If these are the three things that we have, what would be the stopping distance? What would be the distance all the way from here to the far end? If we are able to get the distance from here to the far end, notice that by subtracting this kilometer which is here, we'll be able to find the further distance the train covers after the first 36 seconds so that it stops. So this is the route that we are going to take. So let's find the total distance it covers as it stops. So the total distance it covers, we can again use x. So this time around, we won't use x since we don't know the total time it takes for it to stop. So we're going to use an equation that doesn't use time. V is equals to u squared plus 2ax. I'm using x for displacement again. This will be the total displacement. So here, if I make the displacement subject of the formula, I have v squared minus u squared over 2a. The final velocity, since the train comes to rest this time, will be 0. The initial velocity is that starting velocity, the 34.03. We already found this, so we're just going to square it, divide this by 2 times the deceleration, 0.347. If you work this one out, you get the total distance it travels as it stops. You get this one as 1,669 meters. So this is the distance the train travels as it comes to rest. So in other words, we say from the minute it starts all the way to the far end, the train covers 1,669. But what we want to find is the further distance it covers after 1 kilometer. So in the first part, it covers 1 kilometer from here up to here. It does this in 36 seconds. Our question was to determine the further distance it covers for it to come to rest. So we were looking for this extra distance all along. Notice that to get this extra distance, all we have to do is from the total, from the 1,669, subtract that initial 1 kilometer. And in the end, if we did that, so the further distance it covers, let's just write it as distance. This will be equal to the total distance it covers as it stops minus the distance it covered in the first 36 seconds. And if you did this, you'll find the further distance as 669 meters. So this is the further distance the train covers as it comes to rest after that first 36 seconds. Okay, I hope you guys were able to follow through this, through the solutions or through my explanations. If you've got any comments, let me hear them in the chat section. Otherwise, in the next tutorial, we're going to look at one tricky question. I hope you guys will be able to see that. It's going to be a little bit of a tricky question, but we're going to look at it. So see you guys in the next tutorial. Let me just show you what the question is going to be. So we're going to look at this very interesting question. It is very interesting. It has 2 methods of working it out. Try it out. Let's see how you do it. Okay. All right, you guys. This was your tutor. We'll see you guys in the next tutorial.